thank the organizers for putting together this wonderful conference and inviting me to speak here. And I would also like to thank the previous speaker for putting you in the right mindset for my talk. So it's going to be very related. And it's based on, so the punchline of the talk is based on joint work with Xingtung Yao and Jay Zhao from Perimeter Institute, who's here. And bits and pieces of the talk will be based on work I did in earlier collaborations with these people. So first of all, let me start with a motivation for an introduction for my talk. So there's been a lot of very fruitful interaction between and physics to the benefit of both sides. What I want to focus on today is the interaction between math and physics that came from geometrizing physical couplings. So let's recall the breakthrough of Seiberg and Witten. So they managed to obtain the exact non-perturbative effective action at low energies for four-dimensional n equals 2 gauge theory. And just for the spirit of this talk, recall the way they did this is by knowing leading singular behavior of, or the expected leading singular behavior at various points in the parameter space of the theory or in the manifold of vacua, which could be identified with the moduli space of the theory, and then translating the whole thing into a Riemann-Hilbert problem, which became actually a variation problem of some elliptic curve, the Seiberg-Witten curve. And the point I want to emphasize today, so the Riemann-Hilbert problem or the variation problem for the elliptic curve can be translated into some differential equation. And another point of view which I want to adopt, so if you didn't have information of what happens or what is the leading singular behavior around various points in the moduli space and then patch things together, if you had only at one point the differential equation, then the information would have been completely equivalent and you would have been able to get the full non-perturbative gauge theoretic content of the theory. Okay, so that's a huge benefit for physics because it allows you to get exact solutions. What's in it for math? So the theory of the Seiberg and Witten immediately, so the instant-on questions had interpretations in terms of Donaldson invariance, and that created a lot of excitement. But the interaction with math I want to adopt today is mirror symmetry, which is another statement. So the way I'm going to motivate this is not the way it was historically found, but just let me say that this Seiberg-Witten theory, or the four-dimensional n equals 2 theory, could be obtained from a 10-dimensional theory by compactifying, for example, type 2b string theory on a Calabi-Yau threefold y, and this Seiberg-Witten curve would be some part of the geometry, so actually some degeneration locus of this Calabi-Yau threefold y, and this was found by these gentlemen. All right, so instead of having at each point of this moduli space attached just the curve, you would have attached to each point of this moduli space the Calabi-Yau threefold, and the moduli space in this case would be the moduli space of complex structures of the Calabi-Yau threefold. However, this is not the whole story. What was soon after that also found is that there is another way to obtain the same n equals 2 theory by compactifying type 2a string theory on a different Calabi-Yau threefold x. And this program goes under the name of geometric engineering. So in fact, so there are two ways. So in this case, you would have different or a family of Calabi-Yau threefolds x labeled by some local coordinates on this moduli space. And that would correspond in a precise way to various points in the moduli space of the gauge theory. So, and hence, so from this, you can see that what mirror symmetry says is there is some variation problem attached to Calabi-Yau threefolds y, where M is the moduli space of complex structures. What I didn't say on the last slide, there is some precise identification with a totally different variation problem of a mirror family of Calabi-Yau threefolds. And here the variation problem is called quantum cohomology because it has to do with, it's some variation problem that was developed in order to match the variation problem on the other side. Okay, so mirror symmetry is really mapping variations of complex structure on this side to some quantum geometry on the other side. So that's, mirror symmetry will be implicit in the rest of my talk, so I just wanted to put you in the right mindset to see what this is good for. So the way I want to think about what is the object that you need to compute in order to establish the mirror symmetry and also the relation to gauge theory that I showed on the previous slides, the way I want to think about this is there's some global object that I call Cijk, which can be computed everywhere in this moduli space, and you can expand it in terms of distinguished coordinates in various points. And if you compute the same object on both sides and match them, then the same object would have very different meaning. So here is some of the meanings of this object. So there is an underlying n equals 2,2 superconformal field theory, and in that case, Cijk will be the 3-point function. Cijk is also related to the chiral ring structure constants by the topological metric. So the chiral ring is just a finite ring of distinguished operators in this n equals 2,2 superconformal field theory. So these superconformal field theories can be realized as nonlinear signal models into a target Calabi-Yau threefolds, x or y, and there is a topological theory that can be defined to these, and this is how the relation comes about to the slide that I showed previously. So you can realize this object in two different ways. Okay, so geometrically, what does this object become? So if you forget about the two-dimensional origin of that, Cijk from the point of view of the Calabi-Yau moduli space is just part of the data of a flat connection. So, and we'll see this a little bit further on. So as was mentioned in the previous talk, Cijk, when expressed in distinguished coordinates on the moduli space of complexified Kähler structures, is also the generating function of genus 0 Gromov-Witten invariants. All right, so for the purpose of the talk, I want to motivate, okay, these are not the only global objects that are interesting that you can consider. And I already gave you a motivation by saying this is some genus 0, so this is a correlation function on the sphere. So there are higher genus correlation functions that you can define. And if you package all of these higher genus correlation functions with n number of insertions into some generating function, then this would be what I define to be the topological string partition function. So a priori, the way it's defined, there is some formal parameter here, so it's the exponential of some formal power series that sums over all of these higher genus correlators. It turns out, so these FGs or these correlators will encode the higher genus Gromov-Witten invariants on one side of mirror symmetry, but they can be phrased on both sides. So abstractly, it will be phrased just in terms of the geometry of M. So what I want to say here, so this is topological string theory shares features of physical string theory, and this is why it's also interesting to look at this. One feature that it shares is that this perturbative definition is, or this perturbative expansion is asymptotic. So the question I want to ask today, is there any way that we can make sense out of this perturbative definition away from zero coupling, or is there any way that we can say anything about the non-perturbative structure? So there have been many strategies in the literature and also in recent years of how to address this problem. Most commonly, you can use a lot of dualities by topological string theory is dual to many other gauge theories and also some other things. And then by mapping the problem you don't know to some problem that you know, you can extract information on either side. So one example of doing this in the math literature, so the partition function of topological string theory would be the generating function of Gromov-Witten invariants. So that is the knowledge of all the maps into the target Calabi-Yau threefold X. And there's a conjecture by MNOP which says, okay, there's another natural partition function that you can associate to the same Calabi-Yau X, and that would be the that will be the Donaldson-Thomas generating function, and that will be just focus on X and forget about counting maps into X, but just focus on the special objects that you have in X from the outset. So physically, the counterpart of that is the OSV conjecture. So you have the perturbative topological string theory, and there is another object, the black hole partition function, which you can attach to the same Calabi-Yau manifold, which likewise would forget about all the perturbative definition of topological string theory, but instead would count, would give some statistical interpretation for the black holes created by these special objects living on the Calabi-Yau threefold X. In recent years, there's been a lot of progress made from dualities with ABGM theory and spectral theory by Marcos Marinho and collaborators. So in particular, close to some things that I'll talk about is a recent paper by Marinho, by Grassi, Hatsuda, and Marinho. So, and then there's another technique which had been applied to topological string theory recently, and that's the technique of trans series and resurgence. So there the philosophy is, okay, when you get asymptotic expansions whenever you have some ODEs with irregular singular points, and there is a systematic way of how, so whenever you have an asymptotic expansion, this means that there are some non-perturbative parts missing. So you can systematically look for these non-perturbative parts by making ansatzes and then solving the equation again. So however, the problem of this technique applied to topological string theory is that there is no natural, so the series is asymptotic in lambda, but there is no natural equation in lambda. So, and this is the thing I want to address today. So today what I want to tell you is there's actually, without further input, just from the bare geometry of the moduli space and from the definition of the higher genus topological string amplitudes, we're able to already see some structures. So in some sense, so I'll tell you that the FGs have some very special structure. They're polynomials in some finitely many generators. And there are some universal piece of these polynomials which we can determine for an arbitrary Calabi-Yau manifold to all genera. So it turns out in determining these to all genera, we're naturally led to deriving some differential equation. And this differential equation will be a differential equation in lambda. So in the topological string coupling. Okay, so I'm going to tell you about, so most of the rest will be telling you about what is this special structure that allows us to address this problem. And that's a polynomial structure of topological string theory. First of all, let me recall some notions of special geometry. So special geometry is the geometry of the moduli space. So you can think of this either as the moduli space of the gauge theory or the moduli space of complex structures of the Calabi-Yau manifolds Y, or the complexified Kähler moduli space of Calabi-Yau manifolds X. So if you put local coordinates zi on this, so I goes from 1 to n, then the data of special geometry M has a further line bundle over it, which is Hermitian. So if you choose some trivialization of this line bundle, and you compute the norm of this using this Hermitian structure, and you call this e to the minus k, then k gives you a potential for a Kähler metric on M. So a further data of special geometry are these objects Cijk, which I introduced earlier. So this is, from this way of defining special geometry, just an additional input that you need. And you need this additional input in order to get a flat connection. So if you denote by di the covariant derivatives which are metric compatible, so that's the connection terms of the Kähler metric, and that would be the connection term of the metric and the Hermitian metric in the line bundle, then a combination of this covariant derivative with the action of these objects Cijk gives you a flat connection. So special geometry is the statement that you have a flat connection on the moduli space, or in other words, the curvature of this natural covariant derivatives gets canceled by these Cijks, which are, from the two-dimensional point of view, the Carroll ring structure constants. So if you write this equation out, then you can get an algebraic equation for the curvature of the metric Gij bar on M. So essentially, it's given by this here. So this is the algebraic part, which is given by just these structure constants. Okay, so for the purpose of this talk, I'll just define the topological string amplitudes in this way. So this is the generating function that I had written down earlier. And I'll say that the FG with n insertions is only non-zero if 2g minus 2, sorry, plus n, so the plus is not very visible here, is larger than 0. So you start by defining f0, it should be ijk, to be the amplitude on the sphere with 3 insertions. And then what Bershadzky-Chakotay-Ogurian-Vafa showed is that further insertions are just related to less insertions by taking this covariant derivative. And then you can take as a definition of all the higher genus amplitudes to be defined by what is called the holomorphic anomaly equation. So for genus 1, it takes this form. And starting from genus 2, it takes this universal form. So here is just a sketch. So the way it was derived is using the n equals 2,2 superconformal field theory and having explicit expressions for these FGs as integrals over the modular space of Riemann surfaces. And this is why the whole contribution on this right-hand side comes from the generation loci of the Riemann surfaces. Fine. So what is important about this equation is that it's a differential equation. It's recursive in the number of genera. So everything that appears on the right-hand side is strictly less genus than on the left-hand side. So what Bershadzky, Chakotay, Ogurian-Vafa also did is try to iteratively solve, because it's recursive in nature, so you can iteratively solve this equation. So what they did is introduce potentials for the anti-holomorphic Yukawa couplings or the anti-holomorphic three-point functions. So three derivatives of this object S will give C bar, and the intermediate steps you call Sij, Sj, and S. So the way they solve this is, so now by writing di bar of Sij is equal to this Ci bar, the raising and lowering happens with the metric. You can iteratively integrate this equation. So first of all, you take a di bar out here. And then if you want to write the whole equation, if you want to pull out a di bar of the whole equation, then you pull it out and you have to compensate for this fact by acting with di bar on everything that is written here. So and then everything that happens, so now we have di bar acting on holomorphic covariant derivatives. You can use the commutators or the special geometry relation in order to iteratively get rid of this and then eventually pull out a di bar on both sides. So surprisingly, this procedure led to some, so this will lead to some expression in terms of geometric data, which is entirely specified by all the connections and everything that was in special geometry. But the way it's organized could be mapped to Feynman diagrams. So here's an example from BCUV. At genus 2, you would get Feynman diagrams, and all the handles here would be the objects that are introduced earlier, and all the vertices would be higher genus amplitudes with n insertions. Okay, so this allows you in principle to compute higher genus amplitudes, but it becomes very tedious. So already at genus 3, the number of Feynman diagrams you have to write down is filling a couple of pages. So this situation improved with work of Yamaguchi and Yao, who showed that for the quintic and its mirror, actually the higher genus amplitudes or the Feynman diagram expansion collapses. So instead of being a Feynman diagram expansion, it just becomes polynomial in a finite number of generators. And the generators that they used, so a priori, they took multi-derivatives of the connections that you had in special geometry. So a priori, you would have infinitely many independent functions on the modular space. But they showed that there are actually finitely many of these, and then the derivatives close. So in work with Dominic Lange, we generalized this to an arbitrary Calabi-Yau manifold, and the statement we got is that Fg with n insertions is a degree 3g minus 3 plus n inhomogeneous polynomial in these generators, where we assign some weights to the generators. And the coefficients of these polynomials would be rational functions, as well as some kernel of this recursion will also be a rational function in the modular space. So in order to show this, what we showed is that, similarly to what Yamaguchi and Yao showed, is that if you take derivatives of these generators, then eventually you will stop generating new stuff, so it closes on these generators, and then you can inductively show using the weights and the weights you start with, that the higher genus will be of this weight. So just to give you an example, so here, this is the type of equations that you get. So they're nonlinear in the generators, but everything closes. And the initial correlation function is f genus 1 with one insertion, and it has the polynomial structure, and then the rest follows from that. Okay, so moreover, now you can say, okay, now I know that fg is polynomial, and all the anti-holomorphicity or all of the non-holomorphicity comes from these polynomial generators. So instead of having just one holomorphic anomaly equation, you can split it up in many different equations with respect to these polynomial generators. So this improved the computations a lot. So BCUV had, so for example, if you look at the quintic, BCUV had computed the quintic to genus 2. And then Katzkam and Bafa, using a lot of input from algebraic geometry, were able to compute up to genus 4. And then using the structure at the boundary of the moduli space and the polynomial structure, these people were able to push, in principle, the computation until genus 51. This is really, the problem became, so you can put it on a computer. So furthermore, you can also address more complicated geometries. So just a further comment on this, the structure is not unfamiliar. So already in BCOV, there was a hint. So whenever you have some curves, or whenever you have some SL2Z or some subgroup thereof in your Calabi-Yau threefold, then we know that you would expect quasi-modular forms. And we know that higher weight modular forms are polynomial in some finite degree polynomials and some finite generators. So what we did is also show that this construction matches with the quasi-modular forms. Okay, so however, the punchline that I want to get at today is that there's more you can say. So if you focus on just a one-dimensional slice in the moduli space, so just for combinatorial simplicity, now you can ask, knowing that fg is a polynomial of degree 3g minus 3, you can ask, okay, is there any monomial that you can determine generically for any Calabi-Yau manifold? And the answer is yes. So we look at the highest degree polynomial in one of the distinguished generators. So we want to look at the coefficient of this guy to the power 3g minus 3. So this will be a rational function in the moduli space. And from the Feynman diagrams and from the polynomial structure, we can determine all the part that will depend on the geometry will only be this 3-point function to the power 2g minus 2. And there will be some rational coefficient in front of that. All right, so now we want to ask, okay, what can we say about these rational coefficients? And let me emphasize again that this is universal. It didn't depend. So everything that depended on the particular geometry would be packaged in these polynomial generators. So if you look at the Feynman diagram expansion, then the types of diagrams that would contribute to this is maximal degeneration into just spheres and handles. However, what I told you is that the polynomial structure will also replace vertices by polynomial expressions. So you would also get contributions from all the other diagrams. For example, the 4-point function, if you write it down as a polynomial expression, you would also get contributions. For example, also the genus 1 partition function with one insertion, polynomially written, will also give you some polynomial generator, which is this handle here. And this. So if you collect all of these and then you ask what is the rational coefficient in front of these, this is the question that we're asking. So then we're defining a generating function so the generating free energy of all of these leading monomials, and we just package them with this. So you can think about this, that you're taking a limit on all the other generators that sets them to 0, and you're only keeping this term here. And then you can plug this into the holomorphic anomaly equation and use the knowledge of the differential ring and the polynomial structure and sum the holomorphic anomaly equation over all genera. So what we get is, if you now define the exponential of this free energy and package, so redefine the string coupling by being the old string coupling plus all this part that will depend on the geometry, now you have a generating function of purely these rational numbers that we had. And if you further make some changes of variables, the differential equation that you get is very simple. So if you recognize this is an Airy differential equation. Okay, so what does this equation tell you? This equation will have two solutions. One solution will give you these numbers to all genera, but it also has another solution which doesn't contribute at all to the perturbative expansion. So if you write the solution in terms of modified Bessel functions, then this part here will give you the perturbative part to all genera, and there's another part which doesn't contribute. This is why we put some complex parameter here. What this allows you to do, so maybe zeta is 0, or maybe it's some other value. So perturbatively, you can't determine what this is. You would need information from some other locus in the moduli space. So in particular, having this explicit expression in terms of these explicit functions will also allow you to expand the free energy or the topological string partition function around strong coupling, and you can write down what the coefficients are. But unfortunately, we have no idea so far what to expect for topological string theory at strong coupling. So let me summarize what I told you. There is an intrinsic way of determining, at least for part. So if you had the full answer eventually of topological string theory on any Calabi-Yau manifold, then there is a way to truncate this into a part, which is universal. And you use the polynomial structure of the genus by genus amplitudes in order to determine, well, in order to derive, first of all, a differential equation which can be transformed into an area differential equation which has two solutions. One of them gives you the universal coefficient for any Calabi-Yau manifolds, and the other solution doesn't contribute perturbatively. So as an outlook, what this is suggesting, to come back to the motivation, or hopefully to the motivation I started from at the beginning, is maybe lambda is not just a formal parameter that parameterizes some asymptotic series, but maybe lambda has some geometric interpretation. So maybe lambda, or maybe the differential equation, is a reflection of some variation problem that is going on. And if you had that interpretation, then you would be in very good shape, because then you can go on and solve the differential equation and get the solution at different values of lambda. It would be interesting. So the area differential equation is ubiquitous in many different contexts. So in particular, what I didn't mention here, it's also features very prominently in work of Witten and Kontsevich for the intersection theory of the modular spaces of curves. And area equations also appear in many places of works of Marino. However, this is there it's more natural to expect these, because you often have explicit spectral curves and matrix models where you would expect such type of behavior. Okay, and then of course mathematically it would be interesting if the same perturbative generating function has some other enumerative meaning at strong coupling, for example. Okay, so I'll stop here and thank my collaborators, and also thank you for your attention. That's a good question. So the lower terms, in principle, you could do it also for lower terms, but it just becomes combinatorially. So you mean lower polynomial terms? Yes. So in principle, we just did the easiest part, where it's very easy to throw away and also use the polynomial relations in order to throw away everything else. So in principle, you could also determine the lower parts, but then genus by genus, you would need to keep track of many different things. So in principle, and analogous question is also if you had, so we just took a one-dimensional slice in the moduli space, let's say also generalizing this to keeping track of different labels of these polynomials is in principle doable, but you have to keep track of much more data.
Geometry engineering, what does the limit mean in supersymmetric gauge theory?
What the limit means, I don't know. So I think a way to determine this is probably to maybe, so I don't know, because this is a universal structure, but then you can pick any particular Calabi-Yau. So for example, I think the connection to Marino's work is most promising, where you have some explicit duality to some other part, for example, when you can map this. So the limit that we took is, you can understand as some double scaling limits, or we're taking a combination to be fixed, and then we're sending something else to 0. So there's probably some large n or double scaling limit, but however, I wouldn't know which large n or which gauge theory to consider if you consider the quintic, for example. So that's a difficulty.